Okay, so now I'm good. Now I got a part and I'm ready to do, so I'll go ahead and save. I'll go up to the top left here, hit save, and save all. I want to save all my parts. I want to save this assembly. And now I'm going to go ahead and do a simulation. So for that, I go and hit the simulation tab. This puts me into SolidWorks simulation. New study, I click the little arrow under there, and I do want to do a new study. I don't want a simulation advisor. I just want to go ahead and create a new study. And these are the different types of simulations that we can do. We want to do a thermal, though I think I have to figure out how to do a fluidics analysis, because actually, if this part was very complicated, surprisingly, a fluidics analysis or a Flowworks would be much more efficient. But right now, we're just going to click thermal, and the default name is thermal 1. That's fine. So now you have a tab here at the bottom left that shows we're inside the simulation mode. Now the first thing you want to do is you want to, where it says parts, you just follow the direction here. You're going to go from top to bottom. So actually, why don't we go to the very top where it says thermal 1. We're going to make sure we do a transient. Right now, SolidWorks will do a steady state as the default. But we don't want a steady state. We want to do a transient. We want to see it, temperature versus time. So we go ahead, like I said in the class, right-clicking symbols a lot of times gets you where you want to go. So you right-click here where it says thermal 1, right-click, and what we want to do is go to properties. And we want to change it to one. We're going to make sure we do a transient. Right now, SolidWorks will do a steady state as the default. But we don't want a steady state. We want to do a transient. We want to see it, temperature versus time. So we go ahead, like I said in the class, right-clicking symbols a lot of times gets you where you want to go. So you right-click here where it says thermal 1, right-click, and what we want to do is go to properties. And we want to change it from steady state to transient. At this point, we want to go ahead and do the time that we want to simulate to. Remember, we're trying to get. I want to know how long it takes to cool down from 220 degrees Celsius to 20 degrees Celsius. And I told you that the satellite pass or the Dawn spacecraft pass that we have where we communicate with it it's a 4-hour window. So we don't want the analysis to go larger than 4 hours. We want to go. So right now I'm just going to say 10,000 seconds is kind of good. That's pretty close to 4 hours. So that's 10,000 seconds. And because it's asking you for it in seconds. And then I don't want to do 0.1 increments. That would be 100,000 calculations, and your computer may not be able to handle it. We don't want that kind of detail. So I'm going to put 1,000. So it's basically going to do 10 iterations. Now you might want to do better than that. This is just so I can do a quick analysis while, and not run this video for 10 minutes, And so 10,000 total time, the total time is 10,000 seconds with 1,000 increments, means there's going to be 10 iterations. And that's it. We do that and we hit OK. And now we're in transient mode. Now the next thing you want to do is go to parts here. You click the arrow to open that the parts, and you have the two parts. You have the big one and the little one, or the thick one and the thinner one. And so you need to select a material. So I'm going to go to aluminum alloys. So there's a SolidWorks materials and there's the DIN materials, and I think it's kind of the same. But just go ahead and go SolidWorks materials, click that, go to aluminum alloys, and it doesn't really matter. From a thermal standpoint, they all pretty much have the same thermal conductivity. These alloys and tempers are more from a strength standpoint, but usually if you want to get used to a very common alloy, it's 6061 T6. It's another word for it is automotive aluminum, and we use this for all our spacecraft. This is kind of the main one. There's for if you want larger strength, and there's other alloys, but 6061 T6 is a good one. So you click that and hit apply, and you close. So now what it did is you could see it, and it gave you a little check that you selected material. Okay, you don't need to have a component contact. If you right click I'm sorry, if you go ahead and go to components contacts, it's going to assume that they're bonded together. Some programs will assume that they're not touching, but SolidWorks always assumes that these things are welded. And that's what we want. We want a weldment. We want to make sure this isn't glued. If this was glued, then you'll have to put a connection in here that says, well, there's actually a glue there, and then you have to come up with a contact thermal resistance for that glue. If you guys remember from one of our chapters, I don't know if it was chapter 2 or 3 where we might have been, yeah, it might have been 3 where we come up with contact resistances. But right now we're just going to assume they're bonded. So close that. Now we go to thermal loads, and you're going to have to right click on thermal load, and we want to do a temperature. Remember what I said? You want to assume that that this thing starts off at 220 degrees. This is what we call the cap bed. Now, I don't feel comfortable selecting a surface and saying that temperature is initially 220. I'm sure that's fine. I'd like to select the whole extrusion. So for that, you got to go and you got to go to the feature manager tree from when you built the model. And for that, you have to go to this little bullet up here at the very top, and you can split this window. So you grab that bullet, split it down like that. Now you got your feature manager tree here, and you got your simulation window. So I'm going to select not part 1, but part 2. This one, you can see by hovering over it, it's already giving us a highlight. So I click that whole extrusion, and now I'm going to put the window back up, and it's telling us it's setting us 0 degree Kelvin. That's probably okay, but I feel uncomfortable. No, I'm sorry. Not for the initial temperature is supposed to be 220 Celsius. So first I got to change it from Kelvin to Celsius, and then it converted 0 Kelvin to, now it's minus 273.15 Celsius. I want 220. That's my initial temperature. It's asking if I want to use the time curve. So this is initial temperature. You got to make sure you click this up here, initial temperature, or else it'll hold it at 220 for the whole analysis, and that's not what we want. We want it to start off at 220, and then we want it to cool down. So it's an initial temperature. So hit OK. And the other boundary condition we want to do, I think we said back here where it's connected to the spacecraft, I think we said 10 degrees. We want to hold that at 10 degrees at all times. So I selected that surface. I go to thermal loads, right click, temperature. I just make sure it's not initial temperature. This is a constant temperature. So we leave it at temperature. We change it to Celsius and we say 20. And we hit OK. And you can see it gives you some arrows there indicating that you have a boundary condition there. You didn't get the temperature boundary conditions for the initial temperature because it's not a boundary condition. That's an initial temperature. It doesn't have arrows. So this just means it's always on. It's always at 10 degrees here, regardless of how this thing, and that's fine. That's what we want. And the spacecraft actually tries to hold this at about 10 degrees. So then, now we have, we're not done yet. We need to do the actual environment, right? What's going on? We have radiation, right? So we have to go ahead and right click thermal loads. Now we go to radiation, and I'm going to say, well, both surfaces are actually radiating to space. So I click both surfaces. You can click the surface here, but it's so small it doesn't matter. And now it automatically defaults to surface to ambient radiation. That's what we learned so far in class. This cylinder is going to see cold space, and cold space is not a surface. It's just basically an environment. It's an ambient, but it's really like an environment that doesn't change. It's always at a certain temperature. So we leave that. Surface to surface would be if you had another part this was inside of another part, and you wanted to see radiation exchange, and that's not what we're looking for. So we leave it like that. Now we're going to need to put a temperature of the ambient, and that would be, we'll leave this in Kelvin, okay, because this is cold space. And what I do is I'm going to put 80 Kelvin because space is actually closer to 0 Kelvin. You can put 0. Some people put 3 Kelvin as more of a representation of cold space. 80 Kelvin is what we would do if we put this in a environmental chamber and we want to recreate the coldness of space. We actually have a chamber that we run liquid nitrogen in, and and the walls of the shroud inside this chamber are pretty close to 80 Kelvin. But that's, if you do the math, it's pretty close to 0 Kelvin. I mean, the effects is very small. The difference between 80 Kelvin and 0 Kelvin when you do the temperature analysis is pretty small. So we'll leave it at 80 Kelvin, but by all means, if you want to leave it at 0, you can go ahead. This is the emissivity, and I'm going to pick 0.6 emissivity. This means it's just, you can look at the properties of aluminum at the surface treatment and all that. This is a treated aluminum, and it's what we call chem film. You can look it up if you want to see what's a better emissivity, but I'm just picking 0.6. And this is the view factor. That means how much of this area is being exposed to space, to the environment, to the ambient. If you had some baffles blocking space, like if you had 50% of the view of this blue cylinder thing being obstructed, you would put 0.5. I'm just going to put 1, meaning there's no obstructions. 100% of the surface that I selected can see the ambient. So you can see, yeah, so it's a 1. So I'm going to go with that. That's my view factor, and then I'm good. So I hit like that, and I think I'm ready to go. Now I need a mesh. Create the mesh. Remember, this is actually a finite element solver. In chapter 5 we talked about finite differences. This is not a finite difference program, but it's kind of on a similar concept. Finite element. You right click mesh and just say create mesh. That's going to give you a default setting, and just go with it. Say OK, and that's fine. You don't have to worry about. You just go ahead and hit the default for here. You could enrich it, you could refine it. If you had little holes or certain things that you needed to mesh that wouldn't mesh, you would go ahead and right click mesh and move that little bar to refine it, or pick a number of element dimension, but you don't have to do that for this. And now we're ready. Results is what happens when we solve this. So you're going to go to solve this now. You go to thermal 1, right click, and you're going to run it. It should solve pretty quick because we only have 10 steps. You see, we did a 10,000 second total time span with 1,000 second increments. Let's see how fast this solves. So it's getting there. It's actually taking a little longer than I thought, but let's bear with me on this. So as it solves, yeah, there it goes. So this should be interesting. So total time elapsed was 37 seconds to solve here, and this looks about right. I'm actually a little surprised that there's such a large gradient here. Maybe because of but it doesn't matter. So right now the results, I don't like reading in Kelvin here. So what I do is I'm going to double click on this color bar here, and that opens up on the left hand side my settings. So I'm going to go ahead and go to definition. I'm going to change it. I don't like reading in Kelvin. I like the reading in Celsius. And this right now by default gives me the 10th. This is basically on at the 10,000 second mark, basically the end of the analysis. It shows me the temperature. And that's fine. So now I go to chart options, and I don't like scientific units. I like to see this in just normal floating with 2 decimal places. So I click that to 2, and I hit OK. And if you want, you could, that this is the coldest point right here, and it's saying that it actually dips down to 14.39 degrees C. So which is good. It tells us that we actually reached below 20 degrees. The whole thing reached below 20 degrees by 10,000 seconds, which is, so let's go ahead and now let's do a graph, see the temperature versus time. For that, I'm going to go ahead and I got my results here. I'm going to right click, and so I'm going to go with stainless steel. See if this has it. So I go to stainless steel ferritic, apply, close, and then the other thing is if I go to thermal loads, the radiation, double click on that. I don't think the emissivity is so high. For aluminum, I believe it's 0.3 2. And what else can I tell you? Let's go ahead and run that. Right click on and run. So I'm trying to give me I think I might have made this too thermally well conducting, but you don't have to worry about it. You get what you get. All right, try to follow the project description as best as you can. Everything in there should be, there should be enough information there for you to select materials, select dimensions, and just run it and just report the temperature that you get. How long it takes to get to 20 degrees Celsius. What you might want to do is you might want to select another probe point. You might want to select a warmer, because you want to ensure the whole thing reaches 20. So you might want to select the probe point that is on the warmer side instead of in the middle to get to assure that the whole cat bed is under 20 degrees. Or you might want to select a point out here somewhere, right? Even though I had mentioned it's the cat bed part, the part that's in here that you want to. Oh, the other thing is I'm not sure I have the right mass. So I forgot what the mass was off the top of my head. I'll show you how to measure mass on this thing. So let's go ahead and do the measurement of mass. So let's for that we'll have to go to click model at the bottom, and we'll go to the SolidWorks menu here. You go to tools, and you can say evaluate and mass properties. And now it's telling me that this is 370.92 grams. I'm not sure if that's enough. I don't remember how many grams the other one was. So this is so 455 grams is a pound. So this is like about 3/4 pound or a little bit heavier for this whole system. If the way you change the mass is you can make it thicker, thinner, or you can actually fool around with the you can override mass properties here, and you can go ahead and select, for example, or you can play around with the yeah, you can override mass properties. Maybe it's better to go to what individual part and override the mass property of the part. So go and open the file of this part and change the play around, or there's a bunch of different ways. You can make it, like I said, thicker, thinner to hit that mass. And so again, so let's go back to our simulation. Let's look at it. I'm going to go ahead and probe this. I'm going to select a probe point there, and I'm going to go ahead and map it. I think it's going to give me, so this doesn't make any sense. So let's try something else here. Let's go ahead and do the initial temperature. I'm going to right click and edit. I could have just double clicked it. I'm going to select that surface as well on this surface. Actually, no, let's delete that. I'm going to select the whole part. So part 1. So the whole thing starts off at 220. So put that back up, hit OK. And this will be the last run I do, I promise. So I'm going to go ahead and right click and hit run. So there's different ways of doing this. As I showed you in class, I had the bond line that I had here, you can see it a little bit, was really thin. So there was a very little connection between here and here. You can see this one, this is starting to get isothermal here. This is kind of all like uniform temperature versus this, because remember I changed the material to steel. So steel doesn't conduct as good as aluminum. And so it's now you see less of a temperature gradient. So the difference between here and here is just like maybe a degree now, where it was much larger. And there is a larger gradient between here and here because this is steel. and and actually we are holding this at 10. So let's see. Let's just run with this. I'm running out of battery. Okay, we're gonna have to end this soon anyway. Brighten this thing back up. All right. Okay, this will be the last run. I got the analysis ready. You can right click, probe, click in the middle somewhere, and just map that out. All right, so now we got a better distribution, something I'm more comfortable with. So what you can actually you can screen capture this if you want, but a cleaner way of doing this is to save this as a CSV file, so file save as, and then you would just graph response 1. I'm going to go ahead and hit return, save. Already exists, so yeah, replace it. And now I can go back into my directory and just pull out a Excel readable CSV file and just plot it out, and I can put, accesses. So what this tells us is that we hit 20 around here. So at the 4,600 mark, which is 3,600 seconds, is 1 hour. So it's a little bit over an hour. Okay. All right. Well, thank you for attending this class, and have a good tech week. And I'm going to have a good break myself, and we'll see you next time.